Uh, Ruihang is also a lead of SparseIR project and contributes a large amount of code with me. So today, Ruihang will first introduce the TensorIR project, and then I will give an overview of SparseIR project. So let's start it. Welcome, Ruihang.
Okay, thanks. And hi, everyone. I'm Ruihang, and currently I am a fourth-year undergraduate student from SJTU. And in the past year, I was a research intern student advised by Tianqi, and I just submitted my PhD applications like 1 month ago. And I'm desired to do some interesting and impactful work during my PhD career. And it's my honor to be here today to give you folks a lunch talk. And today I'd like to share our recent work about deep learning compilers. We built a new generation of the intermediate representation for deep learning workloads, and we call it TensorIR. So first, I want to thank all the members of our team. They are from SJTU, CMU, OctoML, and the University of Washington. Currently, more and more people are using TensorIR through the Apache TVM project. So without the hard work of the team members, we're unable to make such an achievement. Let's first take a look at the history of computation hardware in machine learning. In recent years, the mainstream machine learning hardware has changed for a few times. In the beginning, people usually use CPUs as their major machine learning runtime targets. And since 2016, with the rapid development of deep learning and neural networks, machine learning models demand more and more computing power, and GPUs gradually become the main target of machine learning models. CPUs and GPUs mainly do scalar or vector computing, which means they usually compute scalars or compute vectors through vector instructions. However, the machine learning models are continuously becoming heavier, and here is a chart from OpenAI showing the amount of compute used in the largest AI training since 2012. It shows that from AlexNet to AlphaGo Zero, the amount of compute has grown about 300,000 times, and in average, the amount of compute doubles in only 3 to 4 months. So in this trend, more and more tech companies are designing and producing a new generation of processors which use tensors as the first class of computation. Unlike CPUs or GPUs, these new processors or hardware accelerators directly compute tensors. It's good that so many companies are working on high-performance tensor computation accelerators because each accelerator has its own usage scenarios, and it's virtually impossible that one accelerator is general enough and can fit all use cases. However, there are also challenges for deep learning compilers. The most important point is that, unlike vector computing, to utilize the domain-specific accelerators, we often need to call their APIs explicitly. If we will only have one such accelerator, that might be acceptable, but the fact is we have so many, and different accelerators usually have different APIs. So it takes a lot of efforts to deploy a single workload to different accelerators by manually call those APIs. More specifically, to leverage the computing power of hardware accelerators, generally we have 3 steps to go. These tensor computation accelerators usually have their own storage for processing the tensors. So the first step is to load the data from the normal storage to special storage. And after that, we then invoke the computation on the accelerators, getting the computation result. And finally, we load the result back from the accelerator storage to normal storage. And here is a brief example of the use case of NVIDIA Tensor Cores for 2-dimensional convolution. Say we want to use the WMMA functions to compute a 16 by 16 by 16 matrix multiplication. The special storage used by WMMA is called fragment. And thus, firstly, we need to load the 16 by 16 tensors from shared memory to the fragments. And then we call the WMMA sync to compute the matrix multiplication results. And finally, we store the result back to shared memory or global memory. So from the perspective of deep learning compilers, the emergence of tensor computation accelerators urges us to design and build an intermediate representation that fits the trend of hardware specialization. And to design an intermediate representation, there are always two most important tasks. The first one is to easily represent the machine learning workloads, or simply to write a program easily. And the second one is to make the program optimization convenient and efficient. To better understand the tasks or challenges, let's take a look at how one can use traditional methods to represent and optimize a program. Generally, there are two popular methods. The first one is to write the workloads manually, just like you writing a Python code or C++ program. And in fact, this way is widely used by hardware vendors, which provides high-performance runtime library, such as cuBLAS and cuDNN. And another method is to represent machine learning workloads via domain-specific language, or DSL. Most of the time, the DSL itself only describes a computation, and in order to optimize the program, we usually use follow-up scheduling to transform the program. If you choose to write a program manually, obviously you can write every possible or every valid program. For example, if you don't believe the optimization ability of the popular deep learning frameworks, you can choose to write CUDA C++ code to optimize your model. And moreover, if you still don't believe that the MVCC compiler can optimize your program well, and besides you have a lot of assembly code knowledge, you can even choose to directly write the assembly code. So in theory, by manually writing the program, you can achieve any level of optimization you want. But in general, it's not easy to do this at all because it costs too much. For example, companies like NVIDIA and the Intel have hired thousands of experts and engineers to work on writing high-performance kernels and libraries. But even if they have hired so many people on this, only the common operators such as gen or two-dimensional convolution are well optimized. So suppose someone proposes a good operator in machine learning someday. It is difficult for those companies to optimize the operator quickly in short time. On the other hand, if you choose to use domain-specific language to describe a computation and use scheduling to optimize it, indeed, it reduces a lot of efforts from human beings. And the scheduling stage already covers a lot of effective optimization techniques, which sounds really good. But the problem here is the domain-specific language usually has limited expressiveness. You can describe what your computation is via DSL, but you cannot use it to represent how you do that computation. And this problem sounds much more serious today in the context of tensor computation accelerators, because usually people want to directly try to utilize their accelerators without writing a lot of complicated scheduling steps. And from this perspective, the domain-specific language representation is far from enough. So what about we combining the two methods together? A good expectation is that we can write arbitrary program we want by hand, just like writing Python code. And meanwhile, we expect to have a powerful scheduling framework that helps optimize the program at any time. Besides, of course, we also expect the representation and optimization to be friendly and convenient for tensor computing accelerators. So by proposing TensorIR, we aim to reach all the expectations. In TensorIR, we directly represent a machine learning workload or program using a function. We develop a front-end representation of a function in Python syntax, which means people can write their programs directly in Python style, and we can parse or recognize that representation. The front-end representation is called TBM Script, and I will talk more about it later. Inside the compiler, the function is represented in its abstract syntax tree, or AST. If you know a bit about compilers, you may know that a function can have various kinds of representation in compilers. For example, you can use a tree representation to represent your function, or you can use an array of instructions with basic blocks to represent your function, or you can have other kinds of representation. And here in TensorIR, we use the abstract syntax tree to represent the function, which contains more complete information about the function and thus make the scheduling easier. As for optimization, TensorIR provides a powerful scheduling framework that directly manipulates the function in its abstract syntax tree representation. And the intermediate representation as a whole, including the schedule framework, is friendly for tensor computation accelerators. Okay, so the idea of manipulating on AST might sound easy, but in fact, it's not that easy because in the function, there are all kinds of statements. For example, you have loops, you have data loads and data stores, you have external function calls, such as the call of tensor instructions, and so on. And you may have conditional branches. With so many different statements together, the scheduling is challenging. So to make the scheduling easier, we propose the core concept of TensorIR, the block. Generally speaking, a block is an abstract description of a computation. And intuitively, we just wrap a computation by a block. So in this page, there is an example of matrix multiplication with a write-back stage, the cache stage, where the write-back stage copies the computation result from an intermediate tensor to the target tensor. And here we can wrap the computation and data copy on the left side with blocks respectively. You may have noted that there are some changes after introducing the blocks. For example, on the left side, we use I0, I1, J0, J1 as indices to access the tensor C local. But instead, we use VI and VJ to access C local on the right side. And to understand the differences, let me elaborate more on the design of blocks. So, as I said before, a block describes the computation inside. So the description contains three parts. The first part is the iteration domain of this block. And as you can see, each block has several iterators that go through certain axes. The iterators have their own values, which are usually expressions that contain the loop variables outside that block. And most commonly, we have two kinds of axes. In this page, you can see the spatial axis and reduced axis, where the spatial axis can be executed in parallel, and a reduced axis means that along this axis, there is a reduction operation. So in this example, Vy is an iterator of spatial axis, and which equals to y0 times 4 plus y1, and Vx and Vk are similar. The second part of a block is the regions of the tensors that the block will access regarding to the iterators of the block. In this example, the block reads from tensor A in region blah, 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 reads from tensor B in region blah, 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 and writes data to tensor C in region blah, blah. And the last part of the block is the computation body. Unlike the example you saw on the left side of the last page, in the computation body, we only use the block iterators and the variables defined inside the block to access the tensors. And as you can see, here the block body performs a 4x4x4 matrix multiplication. So these are the components of a block. And I said block describes certain computation. And obviously, in this case, our block describes the computation of a 4x4x4 matrix multiplication. You might wonder why the block is designed as this. And one advantage is that by designing the block iterators, we isolate the interior and the exterior of the block. The block interior is linked with the outside world only by these block iterators and their values. And with this kind of isolation, when we manipulate the program outside the block, we don't need to change the interior of the block, except the values of the block iterators. And actually, you can somehow regard a block as a function, where the block iterators are the parameters and their values are the arguments. And this isolation probably benefits the scheduling framework a lot. After explaining the idea of blocks, let's see how the scheduling framework is implemented in TensorIR. Since a block is a description of certain computation, the statements we mentioned before, like the external function calls, the conditional branches, the data loads, data stores, can all be described by a block. Thus, we can simplify the tree we manipulate. If we don't have the concept of blocks, we may have to manipulate the abstract syntax tree, but with blocks, we can manipulate a tree with only blocks and loops in it. For example, in this page, we want to move the block 2 to the position under the loop J0. So briefly speaking, we can just move the tree node of loop I2 and make it a child of the loop J0. In fact, not only the computation movement, but every scheduling operation can be done by mutating the tree of blocks and loops. For example, if we want to generate a cache stage, we first create a block which simply does data copy, and then we create the loops outside that block, and we insert the outermost loop nodes into the tree. And if we want to move some computation, we directly move the block and the other loops of that computation to the target position. If we want to tile the loops via split or fuse or reorder, we directly create some new loops or remove some old loops. If we want to parallelize a loop or vectorize it, what we need is just to update the loop node. So what I'm trying to show is that the block is a powerful design. And with this design, we can do all kinds of scheduling. So what about tensorization? And how do we utilize the tensor accelerators? How do we call the tensor instructions while scheduling? Before talking about tensorization, I would first like to introduce a new operation in TensorIR that is called blockization. So again, block describes certain computation. The computation it describes can be either large or small. For example, on the left side, the innermost block does scalar computing, which is small. In order to utilize the tensor instructions, we want to create some blocks that describes a larger computation or a tensor computation. To this end, we propose the operation of blockization, which helps isolate a subcomputation and create a new block. So in this example, we apply blockization to loop I1. And in the result program on the right side, the loop I1 is wrapped by a newly created block. And thereby, the new block describes a 4x4x4 matrix multiplication. Usually, after blockization, we can then utilize the accelerators by using tensorization. So the idea of tensorization is extremely simple. Let's again revisit the idea of blocks. A block describes certain computation. And therefore, if two blocks are logically the same, logically equivalent, we can substitute one with another, right? That's exactly what tensorization does. So to do tensorization, we first need to provide a tensor intrinsic pair. The pair contains a block of the computation description and another block of a equivalent computation implementation, where the implementation usually calls the tensor instructions. So in this example, we first do loop tiling for matrix multiplication and use blockization to isolate a subcomputation of the 4x4x4 matrix multiplication. Here, the computation description is the 4x4x4 MATML, and we have two implementation on the right side. The first one is to call a special matrix multiplication function provided by the accelerators, and the other one is to compute the matrix multiplication as usual. And when doing tensorization, we first check whether the block to be tensorized matches the computation description. And if so, we will then substitute the block with the real implementation. So after talking about the blocks and how the design of blocks benefits our scheduling, it's time to talk about TBM Script, which is our front-end representation of machine learning workloads. So TBM Script is a Python syntax-based language. You can take a look at the example on this page, and here we define the tensors in the beginning. Then the first block describes a vectorized computation, which adds the data in tensor A by 1 and stores the results in tensor B. And the second block computes the exponentiation of data in tensor B. And I believe that it's so simple that everyone is able to understand. The most fascinating feature of TVM Script is its ability of round trip, which means people can print out a TensorIR function as TVM Script and can write arbitrary valid function in TVM Script and parse it into TensorIR. The main reason why it's easy to understand is that we chose Python as the base language. This is because Python is the most widely used programming language in the area of machine learning. And it's obviously okay to assume that anybody that ever works on machine learning must know Python. So due to the TVM Script's ability of round trip, together with the TensorIR scheduling, which directly manipulates the functions, a feature of TensorIR scheduling is its interactivity. The interactivity basically means after each operation of scheduling, the user can directly print out the current program. And after printing, you can either choose to continue your scheduling, or if you find something wrong, you can stop and check your program. You can even choose to manually tweak the printed program and parse it and schedule it again. So in this example, we create the initial IR module by translating the domain-specific language or by manually writing the workload program. And after each step of operation, we are always able to print the real-time status of the program. So prior to TensorIR, the DSL and scheduling mechanism used in TVM didn't have such interactive feature. So we believe that the interactivity of TensorIR scheduling must bring both users and developers with a much better use experience. And the last part I'd like to share is the extendability of TensorIR. Since TensorIR is an important layer of the TVM compiler stack, besides the technique points, the block, we also did a lot of efforts to make TensorIR easily extendable so that other people in the community can chime in and help develop or maintain the TensorIR together. The first example of the extendability is about the tensor intrinsic pairs. In this page, there are 3 pairs. The first pair describes a matrix multiplication and uses the MMA instructions of NVIDIA Tensor Cores to implement that multiplication. And the second pair describes a single inner product and implements it by a handwritten inner product kernel. And the last one is about outer products. As I said before, to utilize tensor computation accelerators, you only need to provide a pair of computation description and the implementation. And here, both the description and the implementation are functions in TensorIR, or very small scale programs. And it can be represented easily by TVM scripts in Python syntax. Therefore, it's easy for people to add new pairs for tensorization. The second example is that the design of TensorIR scheduling makes it easy to add new schedule primitives. For example, to introduce a new primitive, usually we only need to follow the 3 steps. At the beginning, we check whether the condition of the primitives are all satisfied. If so, we mutate the old statement with the new statement and get the new statement. And the final step is simply the substitution. And we substitute the old statement in the tree with the new statement. And by following these 3 steps, it's quite simple to develop TensorIR by adding new primitives. And the last example is that based on TensorIR, we can even develop new intermediate representation for emerging workloads. For example, to better optimize workloads that involve sparse tensors, Ruihang and I are building sparse TensorIR or sparse TIR, which he will introduce soon. So, in a nutshell, we built TensorIR for better utilization of computing power of special hardware accelerators. And the core concept of TensorIR is the block, which is an abstract description of computation. No matter the computation is small or large, scalar or tensorized. The block is very powerful in TensorIR. Firstly, it simplifies the scheduling, enabling us to only manipulate the tree with loops and blocks. Secondly, the isolation feature of blocks guarantees that the operations outside the block won't affect the interior of the block. And thirdly, the idea of a block describes a computation natively make the tensorization more convenient by simple block substitution. Besides these points, we present the round trip TBM script to represent program in Python syntax, and thus we can make it possible to bring interactive scheduling to bring the interactive scheduling experience to users. And TensorIR also has good extendability for future development. So that's it. And thank you very much. I'd like to take any question. Thank you.
It's a great talk. Thank you so much.
Yeah.
This is awesome work. I wanted to ask a question. Do you think that, okay, so, I mean, I have a lot of questions, but I think my first is, so now people have to write blocks, right? That's going to be kind of, it seems like the hard part of this maybe from the user's perspective is figuring out how to break things into blocks maybe? Like, do you think that there are, for a given kernel, is it obvious how it should be broken into blocks generally, or are there multiple ways to break it into blocks?
Generally, a kernel, you can represent a kernel simply by a single block. And if you don't utilize the tensor instructions if you don't use the tensor accelerators, you can just use one single block to represent the computation. And there is actually no too much need to represent the kernel by multiple blocks.
Okay, so
yeah.
Multiple blocks is used only when you're tensorizing to accelerate your hardware.
Most of the time, it's the case.
I see. Okay.
Like there are also some corner cases, like in for example, in sparse workloads, the workloads that involve sparse tensors, we generally the loops are not independent. Like the inner loops might depend on the outer loops. So in this case, we might use the isolation property of block to better to make the program satisfy some desired property, and to enable the further transformation. So that might be some case that we need multiple blocks besides the tensorization.
Okay. That makes sense.
I believe up to now, the tensorization mostly works in a manual way. It cannot automatically detect if our workload can fit into accelerators. But I have also introduced client side to Ruihang, and we hope there might be some synergy in the future.
Yeah, I mean that's obviously definitely where I'm coming from. Because through Glenside, I've thought a lot about tensorization and thought a lot about how we can automatically manipulate programs to try to discover tensorization opportunities. And so I definitely think about this from a user's perspective of like how much work does the user need to do to get their program to tensorize to various hardware backends. So yeah.
Could you clarify this point? So on tensorization being manual, so because the impression I got from the slide was that it was mostly automatic. So is it reasonable to say you have to specify which passes to apply? How does this work exactly?
So I can switch to that slide.
Thank you.
Yes, it's this page, right?
Yes.
So basically, as I said before, we need to provide the description and the implementation of the tensorization pattern. And to invoke tensorization, you have to specify which block you want to tensorize. So this step is at the very beginning. This step is manually. So you need to manually find the block you want to tensorize, and then provide the description and the implementation, and you just you do the tensorization, and this tensorization just firstly check whether the input block matches the description, and when they matches, you can substitute the old block with the implementation of the pair, the implementation block. So by this way you utilize the accelerators, but this is manual. So the pattern checking is automatic, but you need to invoke the tensorization manually. But actually we are still developing the automatic tensorization rules, so that we hope that the rule can automatically find the tensorization pattern and help do all the needed tensorization.
Okay, that makes sense. Thank you. Yeah. I mean, I've been working with Gus also on Glenside, so yes, that's also the perspective I'm approaching this from. So I have a follow-up question though. So this when you check for a match, is that a completely syntactic check? Like what exactly are you looking for?
I think so. So you basically need the description the description has its own syntax. I mean, the description by providing the description, you write the for example the 16x16 matrix multiplication and wrap it as a description, and the pattern matching check basically checks whether the block you provided are I think they check the almost equality.
It is.
I don't think how to express it clearly because I'm not a native speaker, but I think the check is based on syntax, based on the syntax check, and there might be some corner cases, but since I'm not the main developer of tensorization part, so I don't think I can clearly give you an answer.
Oh, that's okay. Yeah, what I was wondering, yeah, so it would be, so maybe you're familiar with polyhedral compilers, for example. Polyhedral compilers, they take some nested loops, they create this polyhedron, they create a polyhedra structure, and then they can compare to, like, maybe that's something that you could do, compare two different polyhedra, see are they the same thing. That would be one way to do it. But okay, syntax, yeah, I mean that's reasonable. I'll ask around in the TVM community. But no, I really liked the presentation. This is definitely the clearest description of TIR I have heard so far. So I thank you very much for it. Well,
also, sorry, this is maybe a dumb question. TensorIR is different from TIR, isn't it? Or no, it's not.
Are they? Yeah, good question.
They are the same.
Okay.
Oh, it's the same. Oh my God, I should have.
That is what that's what I thought the T stood for.
Oh,
Anyway, I have more questions, but I think I'll let others jump in before I ask them. Thank you again.
Thanks.
Okay, I believe the equivalence check is performed at AST level, so it's almost a syntax level similarity, not a semantic level.
Yep, that's the case.
All right, if no one else has questions, I could ask my other ones.
Well, also see how much time do you need, Zihao? Because Zihao is going to give his.
I will try to make it 20 minutes.
Okay,
Let's go.
I'll hold my questions then, because yeah, we're halfway through the time. More than halfway through the time. I think we should probably move on.
Yeah, Zihao, go ahead.
Okay.